Stephen Hawking, A Brief History of Time, From the Big Bang to Black Holes. Embark on an illuminating journey through the cosmos, discovering a multitude of fascinating concepts as presented in Stephen Hawking's A Brief History of Time, From the Big Bang to Black Holes. Grasp the essence of various scientific principles, such as gravity and the theory of relativity. Develop an understanding of time's relativity and explore the realms of quantum mechanics, spacetime, and the births of stars and black holes, all while diving into the ongoing debate on the unification of general relativity and quantum physics. This book summary lays the foundation for comprehending these complex ideas and connects fundamental forces, laws, and phenomena, inspiring a deeper appreciation for the vast and captivating universe.
Unraveling the power of theories. Theories are fundamental models that concisely explain vast observations, playing a pivotal role in scientific understanding. They stem from collected data and insightful observations, like Isaac Newton deriving the theory of gravity from witnessing the movement of planets and falling apples. These models offer crucial benefits. They allow scientists to make accurate predictions and are always open to reform in the face of new evidence. Thanks to this dynamic nature, theories help perpetually advance scientific knowledge, making science a vibrant and evolving field. Newton's revolutionary laws. Until the 1600s, it was widely believed that an object's natural state was one of absolute rest. However, Isaac Newton shattered this perception by demonstrating that not only were celestial bodies in constant motion, but all objects throughout the universe were as well. In order to explain these findings, Newton established three groundbreaking laws still in use today. His first law concludes that an object will move in a straight line, unless acted upon by another force. The second law articulates that an object's acceleration is proportional to the force acting on the mass. The greater the force, the faster the acceleration, and vice versa. Lastly, his third law delves into gravity, describing how all bodies in the universe attract one another, with the force being proportional to the mass of each respective object. Relativity and light-speed. Newton's theory articulated the revolutionary concept of movement being only relative to other objects. In this context, an individual's speed on a moving train is determined by their relationship to other objects, such as a bystander or a book. However, this theory encountered a problem when considering the speed of light. Unlike other objects, the speed of light remains constant at 186,000 miles per second, regardless of the observer's speed. This perplexing issue persisted until Albert Einstein's groundbreaking theory of relativity in the early 20th century reconciled the speed of light anomaly within the framework of relative motion. Time's relativity unveiled. Newton's theory faced challenges due to the constant speed of light, which revealed that speed is not always relative. Albert Einstein's theory of relativity addressed this issue by arguing that the laws of science remain the same for all freely moving observers, implying that they would perceive the same speed of light, regardless of their own speed. One of the most baffling elements of this theory is the relativity of time. Observers moving at different speeds would measure different times for the same event since time depends on the distance traveled divided by speed. Consequently, time is relative and exclusive to each individual's perspective, which means that two observers would experience the same event happening at different moments, both being right from their viewpoint. Unlocking particle mysteries. Particles, like electrons and photons, are the building blocks of matter. Studying their speed and position to understand the universe becomes challenging due to the uncertainty principle, which states that the more precisely we measure a particle's position, the more uncertain its speed becomes, and vice versa. To overcome this, scientists turn to examining a particle's quantum state that consists of multiple possible positions and speeds. By treating particles as waves with overlapping peaks and troughs, researchers can estimate the particle's most probable location and trajectory, hence shedding light on the mystical nature of particles. In the realm of the universe's building blocks, particles display peculiar behaviors that challenge our understanding of their nature. Electrons and photons, for example, hold crucial secrets about the vast cosmos we inhabit. However, exploring their dynamics is anything but straightforward. Enter the uncertainty principle, a curious phenomenon unraveled in the 1920s. The principle dictates that attempting to determine a particle's position with perfect accuracy leads to ambiguity in its speed, and the converse is equally true. This puzzling interaction complicates our quest to unveil the mysteries of particles. Faced with this dilemma, researchers delved into the realm of quantum states. This innovative perspective encases a particle's myriad possible positions and velocities. Instead of seeking definite values, scientists now consider the variable locations particles might adopt and the speeds they may achieve. To further unravel this enigma, scientists envision particles as waves. With numerous positions forming a chain of oscillating patterns, particles resemble vibrating strings. As they oscillate, they create a web of peaks and troughs that represent various paths they can take. This wave-like perception enhances our understanding of these elusive entities. By examining the alignment of peaks and troughs, researchers identify the most plausible positions and speeds. This phenomenon, known as interference, offers vital insights into the probable course of a particle's journey. Armed with this knowledge, we continue to uncover the intricate secrets of the universe. Grasping spacetime and gravity. The world around us is perceived in three dimensions: height, width, and depth. However, a crucial fourth dimension, time, combines with the other three to form spacetime. This four-dimensional model is used by scientists to describe events in the universe, taking into account that time is relative, as per the theory of relativity. Significantly, spacetime has altered our understanding of gravity. Massive objects, like our Sun, curve and change spacetime, similar to a heavy object placed on a stretched blanket, which causes other objects to follow these curves. This phenomenon explains the circular orbit of objects around larger masses, much like gravity works in our universe. Unraveling the black hole mystery. Stars draw upon vast amounts of energy to emit heat and light throughout their lifetimes. However, this energy is finite and eventually, stars exhaust their reserves, leading to their demise. The fate of a dying star depends on its size, with particularly massive stars giving birth to fascinating cosmic phenomena, black holes. These mysterious entities form due to the powerful gravitational field of massive stars, which prevents their collapsing bodies from disintegrating. As a result, everything is drawn toward an infinitely dense point known as a singularity, the core of the black hole. Black holes possess such immense gravity that they bend spacetime, causing even light to curve along their contours. Their gravitational pull is also inescapable for anything that crosses the event horizon, a boundary beyond which there is no return. Given that black holes absorb light and anything that strays into their event horizons, their presence may seem impossible to detect. However, scientists have devised clever methods to seek out these elusive cosmic entities. One approach involves observing the gravitational effects of black holes on the universe, such as how they influence the orbits of nearby stars. Detecting dark, massive objects around which stars revolve is often an indicator of black holes. Further, researchers look for X-rays and other emissions typically generated by matter as it is drawn into and disassembled by black holes. In this manner, they have even managed to identify radio and infrared waves at the center of our galaxy, which could indicate the presence of a supermassive black hole. The surprising escape from black holes. At first glance, black holes may seem like unyielding traps, with a gravitational pull so strong that even light cannot escape them. It's easy to assume that the inside of a black hole is a place beyond hope, but this couldn't be further from the truth. Black holes are not just cosmic prisons, they're also regulated by the laws of thermodynamics, which ensures a surprising exchange taking place within their clutches. The second law of thermodynamics clues us into this phenomenon. This law states that entropy, a measure of disorder, increases over time. An example of this law is a fire poker, which releases heat radiation as it glows red-hot after it's been in a fire. This principle holds that black holes, too, are not exempt from releasing energy. Contrary to the stereotype, black holes do, in fact, have a way to let heat escape. While it's true that nothing can leave a black hole once it crosses its event horizon, the hope lies in the realm of virtual particles. Teeming near the black hole's event horizon, these elusive particles team up in pairs of matter and antimatter, with one partner embodying positive energy and the other negative energy. When a negatively charged particle is drawn into the black hole's grasp, it can end up giving enough energy to its positively charged sibling to break free from the gravitational pull. The escaped particle manifests itself as positive radiation, while the black hole gains from the captured negative particles. This results in a balance, preventing the laws of thermodynamics from being broken. In fact, this inward flow of negative particles can eventually decrease the black hole's mass and cause it to evaporate. After a long process of evaporation, what remains of the black hole is destined for a dramatic finale, a colossal explosion, as powerful as millions of hydrogen bombs, ending the black hole's reign with a fiery bang. Time's unidirectional nature. Have you ever wondered what would happen if time started running backward and the universe began contracting? While scientists haven't entirely dismissed the possibility, there are three compelling reasons to believe that time only moves forward. Firstly, the thermodynamic arrow of time, based on the second law of thermodynamics, suggests that disorder increases over time. An example of this is a cup falling and breaking; it won't spontaneously reassemble, showing time moving forward. Secondly, the psychological arrow of time, related to memory, indicates that we can remember past events but cannot recall future ones. Lastly, the cosmological arrow of time highlights the expansion of the universe and its increasing entropy. Even if the universe began contracting and the cosmological arrow reversed, we wouldn't know, as intelligent beings can only exist while disorder increases, relying on entropy to break down food for energy. Therefore, as long as we exist, we will perceive time as moving forward. Unraveling cosmic forces. You may be familiar with gravity, the force that keeps us grounded on Earth and makes celestial bodies attract one another. But were you aware that the universe also operates under the influence of three other forces? Electromagnetic force is the powerhouse behind magnetism, and the attractive or repulsive force exerted between oppositely charged particles. This force is much more potent than gravity and plays a pivotal role at an atomic level, such as when electrons orbit around an atom's nucleus. Delving deeper into the microscopic realm, we encounter weak nuclear force, responsible for radioactivity, which only exerts its influence at short distances. As its energy increases, its strength eventually becomes equivalent to that of the electromagnetic force. Lastly, strong nuclear force holds protons and neutrons together within the nucleus of an atom and keeps quarks combined. However, contrary to its name, the strong nuclear force weakens at higher energies. At a certain threshold known as the grand unification energy, all three forces converge and reach equal strength, merging into one singular force that may have contributed to the genesis of the universe. Unraveling the universe's origins. Time, according to most scientists, likely began with the Big Bang, an extraordinary event that transformed the universe from an infinitely dense state into an ever-expanding entity. While several theories attempt to explain this cosmic occurrence, the hot Big Bang model is largely favored. In this framework, the universe emerged from a minuscule point, scorching hot and dense. As it rapidly expanded and cooled, the universe forged the elements present today. Gravity then began its unyielding influence, molding galaxies from clusters of expanding matter. Within these young galaxies, gaseous clouds, mostly composed of hydrogen and helium, underwent nuclear fusion, birthing stars. The spectacular deaths of these celestial bodies then scattered elements throughout the cosmos, seeding future generations of stars and planets. Another intriguing theory, the inflationary model, posits the monumental energy possessed by the fledgling universe allowed the strong nuclear force, weak nuclear force, and electromagnetic force to be equivalent in strength. The subsequent differentiation of these forces unleashed a staggering expanse of energy, rapidly accelerating the universe's growth. Bridging universe's grand theories. To comprehend the universe, scientists have formulated two distinct theories: general relativity, centered on gravity, and quantum physics, centered on subatomic particles. Although these theories offer valuable insights, they are presently irreconcilable, impeding the creation of a unified theory of everything. Quantum physics equations result in improbable infinite values, which disagreement with general relativity's observations. Moreover, quantum theory's concept of virtual particle pairs causes difficulties for general relativity, as the infinite energy they possess suggests infinite mass, which would ultimately result in the universe collapsing into a single black hole. In their pursuit of understanding the universe, scientists rely on two powerful theories: general relativity, which focuses on gravity's impact on large celestial bodies, and quantum physics, which delves into the realm of subatomic particles. While both theories are invaluable in their respective domains, they resist a seamless integration necessary for arriving at a comprehensive theory encompassing all aspects of the universe. One challenge in merging the two theories emanates from the quantum physics equations that produce seemingly impossible infinite values, such as the curve of spacetime, an observation disproved by general relativity. To rectify these discrepancies, scientists strive to introduce additional infinities into their equations. This, however, hinders accurate predictions, forcing them to modify equations to correspond with observable events instead of vice versa. A similar conundrum arises from quantum theory's assertion that the universe's empty space comprises virtual pairs of particles and antiparticles. Their existence generates difficulties for general relativity due to the infinite energy these pairs would possess. As Einstein's famous equation E equals mc squared posits that an object's mass equals its energy, these virtual particles' infinite energy implies infinite mass. Consequently, an all-encompassing gravitational force would ensue, causing the universe to collapse into a singular black hole. These challenges underscore the complexities in uniting general relativity and quantum physics, reflecting the intricate nature of our universe and the ongoing scientific quest to unravel its mysteries.
In conclusion, Stephen Hawking's A Brief History of Time, From the Big Bang to Black Holes has provided a comprehensive and engaging overview of the key concepts and theories that have shaped our understanding of the universe. Exploring topics such as gravity, time's relativity, spacetime, the births of stars and black holes, and the continued search for a unified theory of everything, the book offers a captivating summary of some of the most complex and fascinating scientific ideas. The reader is left with a renewed sense of wonder about the universe and a motivation to continue learning about the mysteries within our cosmic puzzle. As you delve deeper into the field of astrophysics, keep in mind the beautiful complexity and enigmatic nature of the universe, a testament to our collective pursuit of knowledge and understanding.